Hi, everyone. Welcome to the first SNAPP seminar of 2025. Today is our great pleasure to have Chara Podimata. She is the class of 1942 Career Development Assistant Professor of Operational Research and Statistics at MIT. Her research interest lies broadly at the intersection of theoretical computer science, economics, and machine learning, and particularly on incentive-aware machine learning and also social computing and mechanism design. Her research is supported by Amazon Research Award and the MacArthur Foundation through the X grant. She got the PhD from Harvard, and during her free time, she enjoys running and spends time with her dog, Tara. Okay, Chara, our floor is yours. Feel free to take away.
Thank you. Thank you, everyone. Thank you for being here, and thank you for having me to the seminar. So I'm going to be talking about learning in strategic environments, from calibrated agents to general information asymmetry. And this is based on a series of works that we started and completed. We started during my postdoc at UC Berkeley and completed them after I started my job here at MIT. So first, let me start by saying that this talk is going to be about repeated Stackelberg games. So repeated Stackelberg games, and generally like games, are a way to model and talk reason mathematically about interactions that happen between two or more parties, also known as agents, that have, sometimes different incentives or different goals when they're participating in this interaction. So two important applications of Stackelberg games, which are the types of games that we're going to be focusing on for this talk, are on the one hand, Stackelberg security games, according to which the principal, who is the learner, tries to identify the correct patrolling strategy in order to avoid as much as possible the poachers. And then strategic classification is another application that we're not going to be specifically talking about in this talk, but all of our results do apply to these sorts of settings too. So in strategic classification, we have a principal that, let's say it's a bank. They output a classification rule that says, according to your features, this is whether you're going to be accepted or rejected for a loan that you're applying to. And then the agents are going to try to misreport. So instead of reporting their point here, which would be classified as non-credit worthy for a loan, they end up like bumping their feature to go all the way above the classification threshold. So I want to talk a bit more in depth about Stackelberg security games. And this is going to be our running example for the remainder of this talk. Now, the fact that I talk about Stackelberg security games is just for the purposes of exposition. Whatever I say here today holds for general Stackelberg games, which means both Stackelberg games that have to do with discrete action spaces and fully continuous action spaces. So Stackelberg security games is just one small subcategory of these games. So let's see what happens in Stackelberg security games. So in Stackelberg security games, we have two players. One is the principal, also known as the leader or the learner. And the principal, the defender, is trying to identify the correct strategies to place patrolling officers either to the left or the right. These are the two actions that the discretized actions that the defender can have. And then on the other hand, the second player is the attacker. The attacker can decide which target to attack based on what the defender does. And then there is a game matrix here, utility matrix, that describes what each player gains by, for example, if the defender plays left, so they protect the left side, and the attacker attacks the chimpanzees, then both get a utility of 0. If the defender defends left and the attacker attacks the elephants, which are on the right, then the defender essentially only gains a utility of 2 or loses a utility of 2. You can interpret it similarly. and the attacker gains a utility of 4. Just one small question with regards to logistics keeping for this meeting. Am I supposed to be monitoring the chat, or is someone else going to be monitoring the chat and bringing questions up to my attention?
I will monitor the chat.
Fantastic. Good. So let's continue with repeated Stackelberg games and formalize what we just said a little bit more. So we have, on the one hand, the agent's actions. For the purposes of this example, it's just attacking the chimpanzees or attacking the elephants. From the principal side, we have the principal's actions, which are either to protect left or right. And of course, we can have randomized strategies, so like probability distributions over these discrete strategies. So in repeated Stackelberg games, the interaction goes as follows. The interaction happens over a sequence of capital T rounds. At the beginning of each round, the principal comes out and announces a strategy that they're going to play, HT, and this is among the randomized strategies that they can play. The agent observes this HT and gets to play an action YT, which is the best response to HT. And then the principal observes this best response, they observe the YT, and understand the utility that they are obtaining. Now, I've introduced a lot of technical terms here for you, so let me just instantiate all of these terms with a specific example. Let's say that the strategy that the principal chooses to play is HT 30% and 70%. This means that the principal will protect with probability 30% the left target and with probability 70% the right target. So given this HT, which the agent can supposedly observe, the agent's expected utility is going to be either if they choose to attack the chimpanzees, it's going to be 0.3 times 0 plus 0.7 times 2, so 1.4. And if they choose to attack the elephants, it's going to be 1.2. So because the agent, according to what we see here in step 2, the agent is best responding. So they're going to do whatever maximizes their utility. So they are going to choose to attack the chimpanzees. So YT, in this case, the agent's best response is to attack the chimpanzee. YT is announced to the principal, and then the principal computes their utility, which in this case, it's like 2.8. So what is the goal of this interaction? The goal for us is to take the perspective of the principal, of the defender, and try to identify a sequence of strategies H1 through H capital T that try to approach what is called the Stackelberg value. What is the Stackelberg value? For those of you familiar with the concept of a Stackelberg equilibrium, basically it's the value of the Stackelberg equilibrium for T time steps. What is the Stackelberg value or the Stackelberg equilibrium? This is the value that the principal could have obtained if the best value that the principal could have obtained if the agents were to best respond to what the principal does. So let me say this again. The Stackelberg equilibrium is the principal's strategy, the best strategy, such that if the principal were to fix this strategy and play it all the time, and the agents were to respond to this strategy all the time, then this is the value, this is the utility that the principal would have accumulated. Okay? It essentially encodes some form of, it's very similar to like standard notions of equilibrium. The only difference is that we are fixing the order of play. So the principal has to go first and the agent has to go second. Any questions so far? Good. So this is all about repeated Stackelberg games. This is very standard in the literature. There have been many papers trying to optimize these games, to optimize learning in these games. So here's a question for you in the audience now. Is there any assumption in this setup that looks too unrealistic to you? And if yes, please unmute yourself and tell me which assumption that is.
The agents can observe the strategy of the principal.
Yeah, exactly. So the assumption that is too unrealistic is that the agents can observe exactly the strategy of the principal. And this was our starting point for this work here. We wanted to identify a setting, a framework for learning in these like repeated interactions when the agents do not have full knowledge. So we introduced the concept of calibrated repeated Stackelberg games, which are essentially the same exact as standard repeated Stackelberg games, but now the only difference is that the agent does not observe HT exactly, but based on previous interactions, they form calibrated predictions about about what the agent is doing. Think about it as the agent is training a forecasting algorithm, and calibrated calibration is a property for the forecast that tells the agent how close they are to the actual strategy HT that the principal is playing. So then the agent is going to best respond to this PT. Note that PT again may be different than HT. The principal gets to observe YT, which again now is the best response to the calibrated forecast. And then at the end of this interaction, we can allow the agent to observe HT fully. Okay? So far, so good? Good. In fact, you do not need to allow the agent to observe HT fully. You're good even if you give the agent a sample from the HT, because HT corresponds to a probability distribution over different actions, right? It's like 30%, 70%. So it's fine even if you just show the agent a sample from this HT. And again, we want to approach the Stackelberg value. And I know that this may seem tricky or weird at this point because it seems as though I'm comparing apples to oranges. I'm comparing the utility that the principal can get when the agent is best responding to calibrated forecasts versus the optimal utility that the principal can get if the agent is best responding exactly to the true strategy of the principal. We're going to talk about this more in depth in a second. So just as a reminder here, in regular Stackelberg games, we have that the agent best responds to the principal's action directly. They observe the action, they just best respond. And in calibrated Stackelberg games, the agent best responds to a calibrated prediction of the principal's action. So, main first question, which we have kind of like started alluding to, is can we understand how is the principal's optimal utility performing as compared to V star? V star was the Stackelberg value, the optimal Stackelberg value. And then second, I've told you that we assume that the agents form calibrated forecasts, but I haven't told you how easy or hard it is to actually build algorithms for the agents that produce these calibrated forecasts. Because of course, if nobody can produce calibrated forecasts, then there's no point in studying this setting, right? So the second question that we address in this work is, are there natural forecasting algorithms that satisfy our desired notion of calibration, which I'm going to formally introduce in a minute or two. Okay, so what are the main results in this work? Result number one, the principal's optimal utility in calibrated Stackelberg games essentially converges to V star. And we're going to talk in a second about why that is surprising. And then for the algorithms, we show that there are actually parameter-free forecasting algorithms for adaptively calibrated forecasts, both for discrete and continuous action spaces. So for the purposes of this talk today, I'm not going to talk about the second part. So I'm not going to tell you about the forecasting algorithms that we built. I'm going to focus more on the first part. So about understanding the optimal utility that the principal can get in calibrated Stackelberg games. Questions so far? Okay, good. So in order to introduce to you our methodology, I need to give you some more information about calibration. So I have some slides about a quick primer on calibration, and then we will have a quick primer on how do people solve normal Stackelberg, repeated Stackelberg games, and what is the hardness, what is the difference when we jump from standard calibrated games to, from standard Stackelberg games to calibrated Stackelberg games. Okay, so a quick primer on calibration. Roughly speaking, when we say that forecasts are calibrated, we mean that they are unbiased according to their own predictions. So if I say that tomorrow it's going to rain with 30% chance, if I take into account all the days that it generally rains, this is like a 30% of the total like day count. So a crucial notion when we talk about calibration is what we call the binning functions. A binning function pi is defined as for every point in the randomized action set. So there can be infinite number of bins in the standard theory of calibration. And a bin is activated. Activated means that it gets a 1 every time that x for the particular bin corresponds to the prediction P. Okay? So this is basically like almost like a frequency count for how many times you've seen each specific prediction. And so given this, the calibration error is defined with this scary looking function, which I'm going to parse for you right now. So on the one hand, we have to compare the sequence of strategies for rounds 1 through capital T with the sequence of forecasts for rounds 1 through capital T. And then we sum over all the different bins. And the first term is a weighting. What is this weighting? It's the number of times that prediction PT activated bin X divided by the number of times, the number of like actions that the number of time steps that we have interacted for. And this weighting is multiplied by the difference between the average forecast that activates bin X minus the average true strategy that activates bin X. To take a step back, think of it as like, I want to map all my predictions into frequency buckets, okay? So for these frequency buckets, like from now on, you're gonna stop thinking about the predictions as numbers. You're just gonna think of them in terms of their frequency buckets. And then you want to try to identify, the calibration error is the difference between the average forecast that activates a bucket X minus the average forecast, the average true strategy that activates this bucket. And this difference has to be weighed based on how many times essentially you've activated or played each bucket. So that's why you have this term over here. Good. So by the way, calibration, the notion that I just introduced here, it has been known in the literature for a long time. This is my exposition here, the way that I introduced it is just corresponding to the terminology that we use in this paper. But this notion has existed for a very, very long time, both in computer science and statistics. So for the purposes of Stackelberg security games and Stackelberg games in general, we will be defining what we call adaptively calibrated forecasts. What are adaptively calibrated forecasts? So first thing that we need to change is that instead of having binning functions for every possible prediction, and hence having like infinite number of binning functions, we're going to define binning functions for games, where the bins are defined instead of according to the predictions themselves, according to the targets. Now, I want to make this clear here. So previously, if you wanted to do calibration for like standard forecasts, you would add, and you were thinking about, predictions in the 0, 1 line. you would have one bucket for every X in the discretized strategy space, okay? It can be like infinite number of buckets. Here, what we do is we're saying that the number of buckets are going to be the number of targets that you have. So targets 1 through n. And a bucket is going to be, or a bin is going to be activated every time that a prediction makes it so that the best response activates the certain bucket, the specific bucket. Okay? So given this, we define adaptively calibrated forecasts first in terms of calibration error per target. So the calibration error for target I is going to be defined as follows. I'm going to focus on the sequence of principal strategies from round S to round small t, and the principal strategies from round S to round T, the sequence of forecasts from round S to round T. And the calibration error is equal to the average number of times that I have attacked target I throughout the T minus S rounds, okay, times the average forecast that made it so that I attacked target I, minus the average true strategy that made it so that I attack I. And instead of focusing on the L2 norm, here I'm going to be focusing on the L infinity norm. Now, we are going to be saying that we have adaptively calibrated forecasts per target when you can have with high probability that the error for each target is upper bounded by this term R delta T minus S plus some epsilon. And this R delta is going to be the calibration rate. So this calibration rate is the only thing that we assume that the principal knows in this case. Importantly, the principal doesn't need to know the exact algorithm that the agent is using for forecasting, like the exact randomization, nothing. The only thing that the principal needs to know is this calibration rate. And an alternative way of thinking about this is that the principal and the agent, or the principal and the attacker, are engaged in a game where they're both learning, or they're both like playing specific types of algorithms. From the side of the principal, I don't need to know the exact algorithm that the agent is playing. I just need to know kind of like the overall guarantee with which the agent's algorithm converges in some sense. Okay. To put things into perspective, because I introduced to you both standard calibration error and adaptively calibrated forecasts in our setting, I want to contrast a bit calibrated forecasts with adaptively calibrated forecasts, okay? As a reminder, calibrated forecasts is what existed in the literature way before us, and there's a lot of work right now on uncertainty quantification working with calibrated forecasts. Adaptively calibrated forecasts is what we introduced in this work. So calibrated forecasts have a calibration interval of 0 to capital T. Compared to that, our adaptive calibrated forecasts are more stringent in some sense. We need to require that the forecasts are calibrated within each small subinterval. And in a second, not second, but like in 3-5 minutes, I will be able to give you a flavor of the proof that we have. And hopefully you will realize why we need this adaptive calibration and hopefully get some ideas about how we can drop this requirement. Now, in terms of binning, we have already alluded to that, but standard calibrated forecasts, they require an infinite number of bins. However, adaptively calibrated forecasts defined for games specifically, they only require a number of bins that's equal to the number of targets. And now finally, the standard definition of calibrated forecasts, in order to compute calibration error, focuses on the sum of bins, whereas our definition requires that we can bound the maximum over the bins. So that was a brief overview of calibration. I'm gonna wait here for a second about any questions you may have.
Carol, one quick question here. So for the adaptively calibrated forecast here, if for the agents, if the action space is continuous, then the target bins will also be infinite, right?
Yes, exactly. But this is only in the case that you have essentially like a continuous action space.
Yeah. And is there any particular reason why you use the infinity norm in the calibration error?
Yes, it's also going to be kind of like apparent in a second when I give you the proof idea.
Thanks.
Okay, good. So now that we have all become experts in calibration, let me just make you experts in learning in Stackelberg Games, standard Stackelberg security games, okay? So what I'm going to tell you about right now is a general idea about a sequence of many, many beautiful works in this area that try to identify the optimal strategy for the principal H star when the agents exactly best respond to the principal's actions, okay? And my hope here is that by telling you about this literature, we're going to start thinking about how we can adapt these tools into our calibrated setting and what will work and what will not work. Okay, so first, I want to tell you about how to identify H star when the agent utility is known. Now, when the agent utility is known, essentially you know the payoff matrix that I had here on the left side of my slide earlier. And what I claim is that the principal can actually create these best response polytopes. Let me explain what the best response polytope is. So on this axis, we have the principal strategy that is only to protect the elephants. This is a simplex essentially. And on the y-axis, we have the principal strategy that only protects the gorillas. Now, because the principal knows exactly the payoff matrix for the agents, they know where this like cutoff line lies. What is this cutoff line? Well, this cutoff line distinguishes what we call the best response polytopes. So the best response polytope for the chimpanzees is defined as all these strategies for the principal here, that if the principal were to play H prime, the agent's best response would always be the chimpanzee, okay? And the best response polytope for the elephants is this like segment of strategies for the principal, that if the principal were to choose any strategy from within this space, then the agent would always choose to attack the elephants. Now, when the agent utility is known, the principal knows this like simplex and the best response polytopes exactly. And in fact, you just need to solve multiple linear programs in order to be able to identify H star. Why? Because let's focus on the best response polytope for chimpanzees. How can you define this best response polytope here? Well, this polytope is, the objective here is to identify the optimal strategy for the principal, given the fact that the agent always attacks the chimpanzees. And now you need a constraint that encodes why does the agent attack the chimpanzee? Well, the constraint is that for the agent, the strategy of the principal makes it so attacking the chimpanzees is always better than attacking the elephants. Okay? So just solving these multiple linear programs, you can actually identify the principal's optimal strategy H prime, H star. Now, if the agent utility is unknown, then the principal still wants to try to solve for these like best response polytopes, but in reality, you cannot form directly these polytopes because you don't know the agent utility. So you can't really form the constraints over here. And this is the crucial part. So the crucial part is that you cannot identify where is this splitting, where is this changing between moving from best response attacking the chimpanzees to best response attacking the elephants. So what you can do is learn through queries. What do I mean by that? Well, I mean that the principal will literally start like presenting random or like explore random strategies. So for example, the principal can explore strategy HT prime. Once they report strategy HT prime, the agent best response, and let's say that they attack the chimpanzees, then the principal knows that for any strategy that they were to play to the right and below of HT prime, then if the agent was attacking the chimpanzees here, then it would be so that the agent would still attack the chimpanzees if I moved my strategy slightly, okay? And this is also a property that we've seen in, if you're familiar, in other settings like pricing. It's not surprising for you to know maybe that pricing is actually a version of a Stackelberg game that also satisfies the same property of like by queries, you can partition the space and obtain more information about parts of the space as you go. So, okay, back to our learning through queries thing. What we want to do is we want to try to find again this like change, this like best response polytope defining line. So by querying multiple different HTs, multiple different strategies, you hope to be able to identify a path from strategies that attack the chimpanzees to strategies that attack the elephants. And then hopefully at the end, create a line, the polytope line that distinguishes between the two actions, okay? So the whole point in learning through queries is to be able to identify with some good accuracy error the strategy, the line that separates the two polytopes. Okay. So now that we are experts in how we can learn the optimal strategy in regular Stackelberg games, where the agent can exactly best respond to the principal strategy, I want us to start thinking about what happens in calibrated Stackelberg games when the principal is again trying to learn through queries. Okay, so remember that in standard Stackelberg security games, you could learn very well through queries because, you know, once you can ask a clever sequence of strategies and end up identifying the line that separates the two best responses. And we know from many papers in many different Stackelberg games, either Stackelberg security games, general Stackelberg games, or continuous Stackelberg games, like the ones that you normally see in strategic classification, we know that when the agent utility is unknown and the agent is myopic, that you can identify algorithms where the principal's utility essentially converges to V star. Okay, and this is done normally through no regret dynamics. So what we can show is that the regret of the principal's algorithms essentially, when compared to as a benchmark to V star T, which is the optimal utility that the principal could have had if they knew exactly everything from the agent side. This regret as a function of T is sublinear in T. Okay, so when the principal can only interact with an agent that responds to calibrated forecasts, though, note that if the principal plays strategy HT prime, okay, the agent is not certain that the strategy that's being played is HT prime. Maybe the agent has thought or has predicted based on their own machine learning algorithm that the strategy that the principal is playing is PT prime, okay? And sure, it may be the case that PT prime is actually inducing the same best response as HT prime, okay? It may be the case that, you know, even if the HT is something like 0.3, 0.7, and I understand something like 0.1, 0.8, maybe I still attack the same target, and that's fine. Like my forecast has induced the same best response as the actual like best response. This is not always the case, importantly. So there may be strategies for which, especially strategies that are very close to the boundary, the actual boundary, for which when the principal plays HT, it may very well be the case that the agent understands a forecast PT that induces a completely different best response. Okay? Question so far? So here's the crossroads that we're at. It was unclear, and I know that I have kind of like I have betrayed the answer to what I'm about to say because I have told you the main result already. But when we started working on this project, it was unclear to us whether this difference here would mean that the principal can extract more utility by interacting with the agents because the agents cannot fully play as adversarially as possible as they want against the principal, or whether the principal would be able to extract smaller, only smaller, strictly smaller value from this interaction, because it is known that in Stackelberg games, the principal gains by being able to commit. So this commitment power allows the principal to steer the game one way or the other towards what their good outcomes are. So what we show is that, in fact, despite the fact that the principal has this problem of like not being able to fully steer the agents, you can always have that the principal's utility is upper bounded by the Stackelberg value. And the question as to whether this is interesting or surprising, if you know about the learning in games literature, you know that there are a couple of papers that say that if the agent is playing no regret, so if the agent is interacting with the principal, but not with calibrated forecasts, with a no regret algorithm, then the principal can extract strictly more utility than what they could have extracted in their Stackelberg value. Now, is this at odds with what we are proving here? The answer is no, because in these same papers, it was also shown that when the agent is allowed more power in terms of their algorithms, and the more power was encoded in terms of no swap regret, which is strictly stronger than no regret as a guarantee, then it was shown that when the agents have a no swap regret guarantee, that the principal's utility is upper bounded by V star. Okay? So there seems to be something at play here, which I'm going to flag right now, and we are going to come back to it at the end of the talk. There seems to be this like implication of how good the agent's algorithm is tied with the ability of the principal to extract good outcomes. Okay. Let's come back to that at the end of the talk. So I want to give you an idea for the algorithm that actually achieves utility V star minus sub O of t, like a sublinear in T in calibrated Stackelberg security games. And the algorithm is going to look at you from the outside like a version of the learning through queries algorithm that we introduced a couple of slides ago when we were trying to identify the optimal H star. So the algorithm is going to be an explore then commit algorithm. So in the first part, we're going to explore and try to issue a number of clever queries in order to identify an epsilon optimal strategy H epsilon star. And then we're going to commit by playing this strategy until the end of rounds. Now, this is kind of like an easy algorithm. Why is that hard to prove, or why was this like even so technical? So the reason is that because of the fact that, remember, the agent is not responding to your HTs. The agent is responding to what they believe to be the HT. You have a really hard time steering the agents, especially because you don't know exactly the algorithm that they're using. You have a hard time convincing them and steering them correctly to how to identify, how to play against your epsilon optimal strategy. And the problem persists because even if you find the epsilon optimal strategy, uh, uh, oh, sorry, I wanted to yes, so I've already talked to you about that. So even if you find the epsilon optimal strategy, your H epsilon prime, it needs to lie robustly within a polytope. What do I mean by that? Well, essentially, when you have identified a good optimal strategy or approximately optimal strategy, even if you tried playing it for many, many rounds, it would be the case maybe that the agent's forecast would make it so that the agent would start trying to deviate from this strategy, okay? So it wouldn't be the case that it's not always the case that once you converge to one epsilon optimal strategy, if you play it until the end of rounds, then it's going to still be an epsilon optimal strategy. It may be the case that the principles that the agent's action, that the agent's forecast makes them respond outside of this strategy. So in order to deal with this, we actually find an even more constrained property of an epsilon optimal strategy. We find strategies that are within, that lie robustly within a polytope. So these epsilon optimal strategies make it so that the agent would never be able to escape this specific polytope. And we know that because we know their calibration rate. So we don't need to know exactly the algorithm that they're using. Just by knowing their calibration rate, we know that they will always be within this smaller polytope that we have enclosed our epsilon optimal strategy. So once we have identified an epsilon optimal strategy in this polytope, we know that we're good to go for the rest of the time. So putting these things all together is what gives you the regret bounds for this work and the utility that essentially converges to the principles optimal utility. In the last 5 minutes or so, before I open up for questions, I want to talk a bit about where do we go from here. And this is just for the purposes of this paper. So some open questions that stem directly from this work is how can you obtain better convergence rates? So I have very carefully hidden under the rug that our convergence rates for the algorithm that I presented today are actually not optimal. It's like something like big O 5/6. I mean, it's still sublinear, but it's not optimal for sure. And for example, for specific Stackelberg games, so for strategic classification or for pricing, maybe there are better convergence rates that can be achieved by leveraging properties of the specific settings. The second question, which we had a small discussion about in the beginning of the talk, is adaptive calibration really needed? I know that for the proof that I presented today, the proof outline that I presented, we do need adaptive calibration because we want to guarantee that once you are in the small, robust polytope, you're going to be able to stay there forever. You're never going to, you're never going to take an action that's like so far away that's going to take you out of the polytope, okay? And this is a byproduct of the fact that I can control what happens within each smaller interval. But we don't know if there's any information theoretic lower bound about adaptive calibration and why it's needed. And the last question is again from the side of the principle. There's a lot of discussion in the uncertainty quantification literature about who needs to know what and at what time. So it's unclear to me whether you need to assume this R delta, the calibration rate, to be known in advance. Maybe it can be the case that R delta can be learned at least for some specific families of games. And just to do a retrospective about information in games. So far, in this work, we assumed that agents are not myopic, that when they are best responding to the principal's actions, they do not know HT, and we posited that the way that they choose their strategies is by forming these calibrated forecasts, okay? And I showed that when this is the case, then the principal's optimal utility converges to the optimal Stackelberg value. But something that I was expecting, I sometimes expect to be questioned at, is, you know, it's kind of arbitrary that you assumed that agents are going to be calibrated. Why specifically calibrated? Why can't they be any other form of a learning agent? What is so special about calibration? This brings me to the meta questions of what are even the families of algorithms from which the agents can choose to play from? And how do we motivate them, of course? And how does this information affect their and their opponent's ability to obtain nearly optimal outcomes in terms of Stackelberg value? To formalize this into a big question in learning in games, I wanted to understand how can an uninformed player learn to attain the value of her Stackelberg outcome through repeated interactions alone? So to place this into the context of the conversation that we've been having for Stackelberg Games, essentially I want to learn the following. If I have a principal that is trying to learn against an agent, but we don't know exactly the family of algorithms that the agent is using. Can I always guarantee that if I engage in this sort of game, there's always a way for me to obtain my optimal value V star? And the answer is surprisingly or unsurprisingly, no. There has been a lot of discussion, again, in the uncertainty quantification literature about what the constraints should be when two families of algorithms are interacting, so principal versus agents. But you know, we know now at least that it's not always the case that the principal can learn to attain their optimal outcomes no matter the type of algorithm that the agent uses. It has to be the case that the two families of algorithms have certain properties that they satisfy. And with that, I would like to conclude. Thank you very much for being here, and I'll be very glad to answer any questions.
Thank Chara for the nice talk. We have time for a few questions. Feel free to unmute yourself and ask the question. One quick question.
Sorry.
Yeah, just one quick question. So here you don't specify the agent's calibration or the prediction for the forecast, the algorithm for the forecast. So what kind of algorithm for the agents can satisfy kind of the condition that you have this particular rate?
Good. Sorry. Yes. So it can be we know that like calibrated forecasts, we know that if you have calibrated forecasts, we prove in this work, you essentially end up having no swap regret algorithms. And no swap regret algorithms are, just as a reminder, these algorithms where you don't just compete against the best fixed action in hindsight, but you can compete against any best fixed swapping of actions. And swapping essentially means that if you have like actions 1 to 3, a swapping could be that every time that I play action 1, I can switch to action 3. Okay. So we know that when the agents engage in these like no swap regret algorithms, then the principal can can learn like exactly the utility. In fact, we know that when you have a principal that has a full information of the game, like they know some more properties about how the game is organized and whatnot, then the principal can almost always extract full value V star. The problem lies when the principal is uninformed, so they have partial information about the game, and the agent is also uninformed. So they also have some partial information. Think of it as like a Bayesian type of game where they both get signals about the type of game that they're playing, but none of them is like exactly certain about, like what exactly is the realization of the game that they're currently playing. So for these types of games, it's not so much on the what types of algorithms are good for these learning. It's like also what are the families of games and the families of signals that once you're giving this family of games and this family of signals, then people can learn despite, not having full information a priori.
I see. Thanks.
Yeah, of course.
Maybe this is a silly question with respect to the motivation where your work is starting from, but the assumption that the agents use calibrated forecasts, is the principal able to see whether or not the agents are calibrated? And
Yeah, no,
is it reasonable to assume that in practice, given like the applications that you suggest, which are not necessarily algorithmic, if we're thinking about the poaching example, for example?
yeah, so that's a great question. So I will separate my answer to two parts. One is the Stackelberg security games and the poaching example, and the other one is going to be general Stackelberg games, okay?
Yeah.
So when it comes to the poaching example, we do know that poachers are employing some sort of learning, but it's very hard to actually verify what is the closest family of learning algorithms that they employ. So the hope there is to be able to have, guarantees for being able to learn against different type of learning algorithms, and then try to apply them in practice and see which one is closest to being able to protect against the poacher behavior. Now, when it comes to general Stackelberg games, so general Stackelberg games are a lot of times modeled for having algorithms play against each other. That can also be the case in pricing settings. And I think we're going to see even more of that in settings where LLM agents like interact with each other. I think that in these settings for pricing, for example, calibration is something that many pricing algorithms do satisfy from the get-go. In fact, it's not just pricing. Like we show the algorithms that we show that satisfy adaptive calibration are some form of multiplicative weights update with sleeping experts, which are algorithms that we do see in practice. So I guess to, provide a final answer, although we cannot confirm that, algorithms are playing exactly calibrated forecasts, they do something that's kind of close, which is what motivates us to want to study, in principle, in theory, what happens when we are playing against calibrated agents.
Makes sense. Thank you. When Tao also put a question in the chat, you mentioned that the principal agent, the principal gets strictly less utility when the agent does not perfectly best response. Curious how the decrease in principal's utility depends on the calibration quality of the agent.
Yeah, it's that's a very good question. It actually depends on like this factor that I mentioned, the T to the 5/6, is how like it depends on the calibration quality. And there are some other factors in the exponent over there. So indeed, it's true that if your calibration quality is like much, much better, then you can achieve better guarantees and converge faster. But it's not like a huge difference. Frankly, the dominant term is this like T to the 5/6.
Okay, if there are no more questions, then let's thank Chara again for a really nice talk. Hope to see you all in 2 weeks for Peng Yichen's talk.
Thank you.
Yeah.
Bye.
Thank you, Chara.